Anybody know this?
I do.
Bravo! John Travolta's an angel, and apparently he's Michael, the war angel, so he sees a bull in the field and he's like, dude, I think that thing wants to fight, so he goes fights the bull. It's a sweet little bit. And he just loves battle, right? This is awesome. Now you can see what's going on. Where were we? Okay, so what we're going to do, the battle, when acids react with bases, the resulting heat. So, this is important. This will help you understand. I just want to remind you of something. If you take something that's weak, like a weak acid, and it interacts with a base, it's really important you know what comes out on the other side. So obviously, acid and base, does anybody remember? Acid plus base makes water and
precipitate.
Salt, right? But what you need to understand, this is Chem 1, right? Acid and base make salt and water, but now you have a new understanding. Hey, if this thing was a weak acid, which it always is in a buffer, the salt that comes out is actually weakly basic. And of course water is neutral, so that doesn't matter. So don't forget that. That's going to be real important. All right? Now if it had been strong, that would be different. Like a strong acid and a strong base, you just make a salt which is neutral. Remember, the anion of a strong acid is always neutral. So then it would be a totally neutral solution. So that's kind of one of the keys to what's about to happen here. But this is my point. This is a weak base. Okay? Let's see what else I got in here. If I did a weak base plus a strong acid, right? This is a buffer. Now the base is the one acting, right? A buffer always has a weak base component. If it acts with a strong acid, I'm going to always end up with a salt and water, but this salt is always, that salt's neutral, but that acid is always weak. So yeah, so in the neutralization reaction of a buffer, the weak acid always creates weak base, and the weak base always creates weak acid. So this is really good for important to remember when you get into doing a calculation. I'll jump over that. All right. So if I'm doing this, I'm just going to figure out the pH once and my whole point on this is like when I start to treat a buffer, I'm going to figure out the new pH. Because, for example, if I need capacity, I can't drop below so far. Right? So I can figure out the capacity by doing this. So let's just say that I'm talking about using a buffer that has, you know, F minus and HF, right? That's a weak acid, that's its conjugate base. You with me? So then if I start to participate, I'm going to back up here a little bit just so you understand. So weak base, strong acid. So now what I'm going to do is I'm going to attack it with a strong acid. Okay? So now what's going to happen? I'm going to get a little more, right? Anytime I attack it with a strong acid, I'm going to make a little bit more of this. So this is going to start growing. But the strong acid got rid of some of this, so this is going to go away. And how much does it go away by? By how many equivalents of H plus are present. Right? So the change is right here, and that X comes from how many protons are there attacking. So it looks like that. Okay, start with 1,000 mils of 0.5 sodium fluoride HF buffer with a pH of 3.7. So in other words, it looks like this. How many mils of 2 molar sodium hydroxide before the pH changes by 1? So we're working on buffering. So basically what we're going to say is how much 2 molar sodium hydroxide before the pH changes by 1. So I'm trying to get from 3.7. And by the way, if I'm adding sodium hydroxide, what's it going to end up at? If I'm changing by 1, is it going up or down if I'm adding sodium hydroxide? It's going up, right? So how much before this changes to 3.8 is really the question, right? So adding sodium hydroxide will create more F minus, right? Because sodium hydroxide is going to pull off one of these, and it's going to leave an F minus behind. So this is going to grow, and it's going to make this shrink, right? So here's what you're looking at. So if I did the full formula, I would basically be doing this. Whatever I started with, and I'm going to change it back to moles. So it's that many molar per 1 liter times the volume I'm adding, right? Plus N. That's going to tell me how much I'm growing, and this is how much it shrinks. The nice thing about this is because this is on top and this is on the bottom, I can kind of cut it out of there. So I don't need that in my formula.
Where did you get that 0.792 again?
That was the original mix. I just made one up. Like, here's the original buffer. Just to kind of show you how I'd go at this. Right? So it looks like this. This is what your formula ends up doing.
You're converting it to moles?
Yeah, because then I can subtract or add the moles of acid or base I'm adding, correct? But what I showed you in that move was that, hey, there's a lot of this that would just cancel out. So I've now stripped it down. This is kind of what the formula looks like. The pH plus change in pH is pKa plus log of, if you have the original concentration times the volume of buffer you've added, right? And I put it over the, the volume of that you have, plus the N, the moles of this, minus the moles of that. So this basically could work the problem. So if I start with 1,000 mils of 5 molar sodium fluoride HF buffer with a pH of 3.7, so it's this. How many mils of 2 molar sodium hydroxide before the pH changes by 1? Adding sodium hydroxide will remove that and create more F minus. Cool. So I'm going to just plug it in like this. So the formula set, did you have time to get that formula down or not really? Okay, let's back up. Let me just stop there and land. Stop right there. Let's get your formula down.
What is the variable B?
Yeah, so
Volume?
yeah, so that's basically saying this is the volume of the buffer. If it's, and by the way, that should be in liters. So pH plus change in pH. We're going up because we're adding strong base. This is how much capacity I can deal with. Equals pKa plus log of. And I'm just trying to remind you that whatever I put up here for A minus, that's relative to 1 liter, right? So that's always assumed. And so therefore, when you put the volume of the buffer, put it in liters. That way these will just cancel. And then the HA, which is on the bottom, that's assumed to be over 1 liter, right? If it's 4 molar, it's 4 moles per liter, right? So then if I go times the volume of the buffer in liters, basically what I've calculated is moles of HA. What this calculates is moles of the A minus, right? Then I subtract the moles of acid I added, or strong base, and then I add the moles of strong base, and that'll tell me how many moles I can add or subtract. Now remember, Henderson-Hasselbalch, right, basically says it's concentration of A, so if I turned it to moles here, I'd have to divide by the final volume to have it molarity. Correct? Well, since that's on the top and the bottom, it just is gone. I don't need to do it all over again. That's the reason that's out of there. I don't need it. It always cancels out. So this is the formula you need. And you can add this to your book below your acid-base formulas. Now again, what is it for? It's attacking a buffer right? So everybody got it now? Ready to switch the slide and actually work a problem? Okay, start with 1,000 mils of 0.5 sodium fluoride HF buffer with a pH of 3.7. How many mils before the pH changes by 1? All right? So, starting at 3.7, I'm going to change by 1, so it's going to end up like this. It's going to be 4.7 when this is done. You know. Everybody okay with that? Equals pKa. That's based on the HF. Sorry. It started off at 0.792. And how much of that stuff do I have? Happens to be a liter, which is great, because that just, right, times 1. And then plus N, strong base. And on the bottom, 0.5. Got a liter of this stuff, minus NSB. I'm trying to solve for this. How many moles of this can I add, right? So what do I do? Mathematically, does that make sense how that setup came? And again, you'll have this formula in front of you, so it'll be helpful. You don't have to memorize that one. What do I do mathematically to solve for the moles of sodium hydroxide I can add? How do I get N? How do I solve for N? Yeah, get this moved over, right? Let's get that moved over. We're going to be at 1.2. The log of this whole mess, right? And what do I do to both sides to fix that? Raise to base 10. Right? Not so bad. 15.85, you agree with that? Yep. And then I'm going to cross multiply. I'm going to take this over here and multiply it out. Put a sulfur in. What do I do now? Move this to the other side. It's going to be 16.85 in. This goes to the other side, subtracts. Good stuff. Last move, n equals. Is that making sense? Now the question though is how many mils of 2 molar sodium hydroxide? So I gotta add so much of that till I get to 0.424, right? Right? So I get to add that many moles. So I gotta think about 2 moles per 1,000 mils times Y equals 0.424 moles. And I don't have to worry about it diluting in the mixture. It's just, that's how many moles I'm adding. Agree? Y equals 424 divided by 2, right? 212. You with me? The key of this is just understanding this, and you're kind of plugging and chugging, right? So let's walk it through and just kind of make sure we understand that. I'm adding a strong base, right? So that means that the pH is going to be up. It's going to add. Whatever I'm trying to worry about change, it's going to go up. So that's added on here, right? This is actually solving for moles of the base I'm adding. So this is what I'm after. I do have to incorporate how much buffer I'm dealing with. Do it in liters. Then really it's plug and chug beyond that. And just so you know, what am I after here? I'm just basically saying you now have the capability to say, hey, if I got to keep that buffer within 1 pH unit, I can calculate how much of this base I can have. That's how much capacity it has for that, if I want to stay within 1 pH unit. We kind of need to be able to add a strong acid. Right? Same concept. Let's adjust the formula. You guys help me so we can get it in our book right. Again.
So if we're making it more acidic, is it going to be minus or is it going to be
There you go. So I'm starting with pH, right? I'm making it more acidic. What's it going to do to the change? It's going down, so what happens here? Minus the change in pH, right? That's the formula. Everything else is looking the same, right? Plus log of, you know, the A over the, you know, that's always 1 liter, times the volume of the buffer. Now what's going to happen to the, so when I attack with a strong acid, it's going to consume this, and it's going to create more of this. Make sense? So then these just change signs. Right? There we go. There we go. And that's your formula for doing the other. So put that in your, you know, formula book. Adding nitric will remove F minus, thus creating HF. Right? I don't know if that's making sense to you. I just want to make sure you understand. HNO3 plus a base is going to protonate that base, right? So it's going to make HF,
And then
and it's going to consume. It's going to make this go away and make that grow, and that's why we're doing that the way we're doing it. So. And if you want, I just changed it all to mils. That way I didn't have to mess with liters, right? You could do it this way. Go that per mil and then go times 550 mils. It'll still work the same. You can do it that way if that makes better sense to you. And again, I work it out just so you can see. These are moles. I have to divide them by the final volume, but since I have to do that top and bottom, this doesn't matter. I don't need to deal with the final volume. It cancels out of the equation. So it look like this. Same sort of problem. Solve it out. Next move, multiply this over, right? And distribute. Raise the power of 10 first. Then multiply this over and distribute. And then collect terms. And then you gotta just walk it back and go, okay, that's that many moles of nitric acid, right? And I'm adding 1.5 molar nitric acid. So back to solution world, we're like, okay, how do I, knowing I have that many moles of HNO3 and then use that like a conversion factor, right? I'm going to just do that piece over here. .338 moles HNO3, right? And I'm going to use this like a conversion factor. Oh, it's 1.5 molar. That's 1.5 moles per 1 liter of solution. Correct? It's going to cancel, and it's going to give me watt for a liters of solution I need to add. Or since it's asking for the answer in milliliters, you can make this 1,000 if you want, right? What's the final answer?
0.225.
Or
225,000.
That's your capacity formula.
Okay, so this one is wrong.
And if you watch the videos, like when I talk about capacity, I did it differently. It was just this raw capacity to where you got to where the peak drops. But I realize, like, depending on what you guys are doing, you might have to know this. Like, I can only adjust the pH, 1 pH unit, or only a half pH unit. Now you know how you can do that calculation. Good stuff?